Hello everyone, welcome to the next set of questions from the June 2021 CSIR-NET question paper. So, we will be doing the question number 25 to question number 30. So, let us look at the first question. The question says, the structure of a reactive intermediate generated by reaction of chloroform and KOH. So, we know this reaction very well. This is used in Riemann-Tiemann reaction. So, to prepare dichlorocarbene, right? These are the structures you are asking for the one. So, very clearly first step is OH minus takes away this proton, you get a anion, and we know anions are sp3 hybridized. So, you get a sp3 hybridized and 2 electrons are in the sp3 hybridized orbital. Second step, what happens is actually this Cl minus leaves. So, when minus leaves, kind of carbocation is formed. So, carbocation, sp2 hybridized. So, you are having a p orbital. Now, this p orbital cannot gain electron from the carbanion part. So, this is the basically structure, and what happens is to this unhybridized p orbital, it gets stabilized by the 2 chlorines, and that is why they are quite stable, and it has been even isolated and characterized, right. So, thus the answer is option number B. Moving on to the next question. The next question says, the reagent that will affect the following selective conversion is. Now, this is pretty niche carbohydrate chemistry question. Luckily, I have done my PhD and my postdocs in carbohydrates, so it is simple for, but it is not very simple question, but there is a way to find out. Let us see what are the groups are there. So, this is the OPMB group, O paramethoxybenzoyl group. We will do this. This is a specific protecting group, and these are common. These are benzoyl, this is benzyl, and this is acetate, and this is methoxy. So, what we are going to do is I am going to talk about each reagent separately, so that you appreciate which of them will remove what, and then finally we will come to the right answer. I can tell the right answer right away, that is DDQ, and I do not think you would have studied in your undergraduate or postgraduate. If you studied, well and good. Okay. So, what are the groups we are having? We have acetyl at position 2. You can see here at position 2 you are having acetyl OCOCH3. So, it is a ester group. At position 3 you are having benzyl, it is a ether, beautiful protecting group. It goes out easily in hydrogenation. So, it is a catalytic hydrogenation. You have to just put balloon with hydrogen, and down you have to put palladium catalyst on charcoal. So, very mild condition, but otherwise it is very sturdy. It will not get removed even in acidic or basic condition. At position 4 you are having benzoyl ester, is again an ester. You can see R O C double bond O PH, and position number 6 is what we are interested in, OPMB, paramethoxybenzoyl. Okay. So, at para position you are having methoxy and you are having benzyl, not benzoyl, I am so sorry, it is benzyl. Okay. OCH2PH. So, it asks how do you separate, how do you remove it. So, let us look. The first reagent is sodium methoxide. Sodium methoxide is a powerful base. Generally, we prepare in situ. We just take methanol and in that we will put sodium, how much ever equivalent we need it. Okay. So, what it does, it removes all the esters group. So, this goes and attacks here. So, this is the R group, this is the carbohydrate group, on that we have. So, this the pi bond goes up, comes down, and this leaves, and you are getting RO minus. So, that is how we protect. So, OMe minus will be used for protection of deprotection of your acetyl and benzyl, benzoyl, yeah. It will protect both acetyl and benzoyl, not ether, I am so sorry, it is ester. Okay. Next question, next is option B. Option B, what is the option B? Option B you are having TBAF, THF. So, basically TBAF is tetrabutyl ammonium fluoride. So, it is all about giving F minus. Now, if I put sodium fluoride, it will not dissolve in organic solvent. So, I will not be able to put F minus in the system. So, that is why we use organic salt. So, we use this. So, we are having F minus. Now, F minus is a hard base. It is all about charge interaction. So, if you had something like silyl protecting group, silyl is a lot of positive charge because it is more electropositive than your carbon, and so it would have been used. Here does not look like you would have removed any of the protecting group which has been given. So, C is the right answer. So, let us leave that. Let us look at option D. Option D is triethylamine. You can see this NET3. Now, it is a very uh, weak base. Okay, not very weak, but yeah, it is a weak base. It will not deprotect any of them. So, of course, the answer is DDQ. So, let us understand how DDQ basically works. This is what is DDQ, dichlorodicyanoquinone. So, you are having this quinone and dichloro and dicyanose. I hope everybody remembers this. This is the quinone. It is prepared by dehydrogenation of your phenols. Okay. So, this is your sugar part and this is your protection group. So, first H minus comes and attacks here, this comes here, this comes here. All the driving forces because it becomes aromatic. It's a big driving force. So, that actually this goes and attacks here, this arrow is missing, this goes and attacks here and this goes and attacks here, this comes here, this comes here and you are getting this, right. And then water in the workup, this will go and attack the carbohydrate, this leaves, and that is how you get your carbohydrate back. So, thus answer is your option C. So, there are some indications that actually DDQ works by single electron transfer, but yeah, DDQ is the answer. Question number 27. Now, this was tough question, it took pretty long time for me to do it. So, the Newman projection given here is there correspond to the compound A, B, C and D. So, first what we have to do, we have to draw the stable conformation. This is 2 cyclohexane attached each other, it is a decalene system and we do not know it is transdecalene or cisdecalene, that is what we have to find out. Here interestingly all of the structure given are cisdecalene, so we clearly know it will be cisdecalene, but we will do one by one. We can see here both the hydrogens are away from the viewer, that means the rings are cis to each other, so it is a cisdecalene system. Now, only thing we have to look at the other functional group, other substituents. Okay. So, we know this much that in Newman projection when you are having something like this, so this front part is like towards the viewer, so all this H1 are towards us and all these H2s are behind us. So, this is the structure. So, you are having 2 methyls here and you are having 1 methyl here and that is it. So, what we have done, I have done here is I have numbered them. So, 1, 2, 3, 4, 5 and 6. So, 4, 5, 6 are behind. So, 1, 2 and 3 are front, 4, 5 and 6 are behind. Okay. So, we can show it like this, 1, 2 and 3 are front and 3, 4, 4, 5, 6 are behind. Now, let us look at CS3 at carbon number 3. Carbon number 3, what happens? You can see H is, this H is above the plane and this CS3 is below the plane, correct. So, even in the chair conformation we have to draw hydrogen above the plane and CS3 below the plane. Now, 4 anyway both are hydrogen, 5 anyway nothing is a CS2. At 6 we can look, CS3 is above the plane, hydrogen is below the plane. So, that is what we have to remember. In carbon number 3, H is above the plane, CS3 is below, and on carbon number 6 is other way around, CS3 is above the plane, hydrogen is below the plane. So, what we have to do? We have to look here that at carbon number 3, hydrogen is above the plane, should have drawn axial, became bit tedha. Actually, I did not draw, I asked somebody else to draw, so this became problem. And then CS3 you can see below the plane, so it comes in equatorial position, very clear. Okay. At carbon number 6, what happens? We saw that methyl was above the plane. Now, you can see here, this is the pointed carbon. So, please understand how do we draw axial. So, to reach this carbon, I am going down, correct? I am going down this side also. So, the axial will again be down. So, straight line axial. So, hydrogen is below the plane, equatorial will be above the plane. Okay. Then, carbon number 1. What happens at carbon number 1? At carbon number 1, we can see hydrogen is below CS3, sorry, the ring is above the plane. See, I have cut it so that it is very clear that this part and this part is not joint. Okay, this part is joint, this ring extension. So, we have to draw them above the plane. So, this carbon 1 takes to 10, carbon 6 which I was telling till now CS3 was basically another ring. So, this is coming. So, this is again above the plane. So, number 7 and number 10 both are above the plane and you are getting this. So, at carbon number 8 what happens? At carbon number 8 let us see. At carbon number 8 this is the one. So, H is above the plane, CS3 is below the plane. So, here also we are doing this. H is above the plane, CS3 is below the plane, that is why H is coming in axial position, CS3 is coming in equatorial position, and therefore we know that it is a cis-decalene system. And At carbon number 3, CH3 is below the plane. At carbon number 8, CH3 is again below the plane. That means both of them will be in same plane away from the viewer. So you are having both this CH3 and this CH3 away from the plane, away from the viewer, and this hydrogen away from the viewer because it is cis alkane. Thus the answer is option A. Okay, maybe I'll just go slowly. You can read it and you can pause and read it. Okay. So this is the question. These are the options. Takes time. Please use pen and paper to understand this. Okay. So once again I'll tell you, this was not CH3. I talked about CH3, but it was basically the ring extension. Okay. This also was ring extension. Okay, moving on to the next question, question number 28. So it says the major product in the following reactions. You are having an alkene and you are having a diketone, and the catalyst used is titanium isopropoxide. It is effectively a modified form of ene reaction. You know what is ene reaction? Ene is basically alkene is there, ene is there, and plus enophile is there. Enophile is you are having allylic hydrogen, right? So the HOMO of ene interacts with LUMO of enophile. So this goes and attacks here allylic hydrogen basically on the alkene next carbon, whichever hydrogen is, that is allylic hydrogen. Okay, so this comes in, this gets, and it goes to a 6-member transition state, and these two moieties join together. That's what happens in reaction. Here what is happening is basically your, instead of alkene, ketone is interacting, one of the ketone, because one is ketone, one is ester. You can see here, sorry, it was not diketone, one was ketone, not ketone, aldehyde, other part was ester. So aldehyde part is reactive, which takes part in the reaction. So this is what reacts, and definitely ester cannot react, and what happens is this will go, now it goes to chair conformation because that is what is stable. So this comes up, this comes here, and this oxygen will take away proton like that, this goes and attacks here, and that's what happens. You can see here, and you're getting this product. So answer is option number D. Next question, the major product formed in the following reaction is. This is very simple. As soon as you see something like alene or ketene and along with it another alkene, it has to be 2+2 thermal addition. So now we know 2+2 pericyclic reaction cannot occur under thermal, it occurs under photochemical conditions, but in allyl or ketene it is possible because molecular orbitals start matching. What happens actually is, if you look here, it will be plus and minus, okay, plus and minus. So imagine if this HOMO is reacting, so this will be, both will be plus plus, and this LUMO is reacting, so we are having plus and minus. So we are having plus and minus. One second now. Yeah, so we are having plus and minus. So this cannot react. This plus will interact with plus, but plus cannot interact with minus. But what happens? What happens is another alkene is also there here, right? So in its HOMO also you will be having, sorry, in its LUMO also you will be having another plus and minus. So they are 90 degrees to each other. So this comes in between them, and that, so that this plus can interact with this plus, and this plus can interact with this plus, and therefore 2+2 thermal addition is possible in allenes and ketenes. Okay, allenes and ketenes. So now this is a very straightforward concerted reaction. The stereochemistry of reactant will be maintained. Very clearly you can see here that this is a transalkene. This is a transalkene because both COMe are away from each other, two hydrogens are away from each other. So of course product will be this one, no doubt about it. Okay, so let us look at the mechanism. So that's what happens. One doubt you can get, that whether to attack on this part or this part. So please remember, always statically less hindered side will be attacked. It is all kinetic driven. We know about others also, endo rule and all. Pericyclic reaction is always kinetically driven, so it will not go and attack towards this side. This is the less hindered side, so this goes and attacks here, this comes and attacks here. So one OME will be towards, one OME will be away from the viewer. Thus the answer is option B. Option B, I thought option C. Oh, okay, I did not see this, but yeah, this also was trans, so option B. Okay, right. Next question, the major product formed in the following reaction is, now this is simple reaction, this is of course 4 plus 2 addition, it is pericyclic reaction, cycloaddition. Only thing is asking about the stereochemistry and the regioselectivity. So we know HOMO of diene interacts with LUMO of dienophile. So first attack will be, we have to look at that carbon which has maximum electron density. You can see here this will pump electron, so this will pump here. So you are having maximum electron density here. So you have to always look at the carbon which is having maximum electron density. So here also CS2 is there. Benzyl actually armed group, so it will pump electron, it will pump electron. Again you can see here is the first one. So this will interact, and here we have to look at the electron poorest center. We have to look at delta plus. So you know nitrogen is more electronegative than carbon, so of course nitrogen pull away electron, so you will have less electron density here. So that's what attack will happen. Also OTS, we know OTS is nothing but a tosylate group, which I will show you down, but basically this helps in electron withdrawing group. It is maybe I can show it to you here itself. Tosyl is nothing but OS double bond O, sorry not O, because I got confused with O tosyl group. Generally we put O tosyl, but this is N tosyl. So what happens is here, one second, here what happens is, here there is a sulfur and you are having double bond O, double bond O, and you are having here benzene with CH3, because it is tosyl means there will be a CH3 toluene group. Okay, so that's what, so it helps in removal of electron density from the ring. So lot of positive polarity, so this has to interact with this, so that this goes up and this will interact with this. So this explains the regioselectivity. So let us look, please read through it slowly. What all I have said, it's there. So these are the electron rich centers in diene. With all that it fitted that, and this is for dienophile electron withdrawing group. So this is where the positive comes, right? So all that I said is here, and therefore we have to look for this first. This will attack the electron poorest center of the dienophile. So we are having this as this one. So what you are going to do is, we have rotated it so that this electron rich center comes to the electron poor center, and this comes and attacks here, this comes here, this comes here. So our ring is done. Now only thing we have to find out is the stereochemistry. Now we know what is called as endo rule. Now what happens is, let us look at this carbon. So this carbon is like this, and you are having N, TS, TS. Now there is a COOET. So this COET, this carbon has a p orbital, right, which is forming pi bond with the oxygen. Now if this p orbital interacts with this p orbital, this is called a secondary interaction. Primary interaction is, of course, these two are interacting, that's why bond is being formed. These two are interacting, that's why bond is being formed. This is primary interaction. But if this interacts with this is called secondary interaction. It makes the reaction fast, so it is kinetically driven, and therefore just let me rub it, reaction will not happen in a way that CO2 is facing this side. It has to face other side, so we have to rotate it. So what we do, we rotate it, so that it comes this side, and so that this is able to interact with this. This is the secondary interaction, and this is the primary interaction. Now what happens, how do we know the stereochemistry? Try to look like this, you are looking from this side. So what do you see when you are looking from this side? What you are seeing is this hydrogen, and this TS is towards you, towards the viewer. Anyway, this TS will not make a difference, because there is no second functional group, no second substituent here. So that question does not come towards the viewer, away from the viewer. But here clearly, if you are looking from this side, hydrogen is towards you, CO8 is away from you. Similarly, this methyl is away from you. But anyway, if double bond comes here, this methyl remains in plane, so it does not matter. So all that what matters is this COET is away from you. Okay. Also what matters is this hydrogen. Here there is a hydrogen, and then you are having CH2OBN. Please understand, you are looking from this side. So looking from this side, what happens? Hydrogen is coming towards you. This is away from you. Clear? So this also will be away from you in the, away from the viewer in the answer. So your answer will be, see this part, hydrogen towards you, this is away from you, and this CO8 is away from you. Okay. So that's what answer is option number D. So that's it for today's class. Thank you very much.